We will be covering functions and relations. In the next videos, we will cover relations, functions, including one-to-one functions and onto functions, and Stirling numbers. We will skip the special functions in your textbook. We will continue with pigeonhole principle, and then function composition and inverses. Relations and functions are the two topics covered in this video. In the next video, we will continue with functions and go on to pigeonhole principle and function composition and inverses. So we'll start now with relations. And we'll start with the definition of the Cartesian product. The Cartesian product, also known as the cross products of sets A and B, written A cross B, equals ordered pairs A and B such that A is an element of A and B is an element of B. These ordered pairs AB can be interpreted as points in the Cartesian plane. For our first example of a cross product, we will look at the sets A, which is equal to 1, 2, 3, and B, which is the set 2, 4, and 5. So we'll need to start writing all the ordered pairs where the first element is from the set A and the second element is from the set B. So we'll start with 1 from set A and 2 from set B. And then we'll continue with 1 from set A, we already have the 2, and then we'll pair it with 4 and 5. So we have another 1 from set A and 4 from set B, as well as 1 from set A and 5 from set B. Next, we'll look at the second value of A, which is 2, or the second element of A, which is 2, and pair it with B's 2, 4, and 5. So we'll get 2, 2. Our first question is, what is the cardinality of A cross B? So we listed out the elements of A cross B. Essentially, we had a two-step process. The first was to choose an element A from set A, and our second stage was to choose an element B from set B. So we are doing two stages, and we will be using the product rule. So again, our two steps are choose an element of A and choose an element of B. So the cardinality of A cross B is going to be the cardinality of A, since that's the number of ways we can choose an element from set A. We're going to multiply by the cardinality of B, since that's the number of ways we can choose an element from set B. There is also a generalized Cartesian product for n tuples, so you can have A1 cross A2 cross etc. up to A sub n. And that's basically the n tuple where each A sub I is an element of the set A sub I. We've seen this example where the set A is equal to 1, 2, and 3, and the set B is equal to 2, 4, 5. The cross product is this matrix here, where the first element comes from set A and the second element comes from set B. Again, this first element is from set A and the second element is from set B. Here we have set A, set B. And then we keep going. Set A, the 2 from set A, and the 2 from set B, etc. Now we come to the definition of a relation. A relation A on B is any subset of A cross B. So here, looking at A cross B, any subset. So it could be the empty set. It could be 1, 2, 2, 2, and 3, 2. It could be 1, 4, 1, 2. So the question is, how many relations are there from A to B? Well, given that the cardinality of A cross B is the cardinality of A times the cardinality of B, so there are this many possible pairs to put in the relation. So for each of those pairs, we decide whether or not to put them in. So there are 2 to the A, cardinality of A, times the cardinality of B, because for each of the ordered pairs, we have the decision to include it or not include it. So 2 choices. At each stage, we look at one of the pairs and decide whether or not to include it. And one more word on notation. If 1, 2 is in the relation, we say that 1 is related to 2. In this case, 1, 4 is in this relation, we would say that 1 is related to 4. We have a theorem about cross products. So A cross B intersect C is equal to A cross B intersect A cross C. A cross B union C is equal to A cross B union A cross C. We have A intersect B cross C is equal to A cross C intersect B cross C. And then A union B cross C is equal to A cross C union B cross C. To be honest, I haven't had much occasion to use these theorems, but they are there for you in case you would like to use them. So now we've covered relations, and we're ready to go on and look at functions. A function, also known as a mapping, f, from a to b, notated with this notation, f is a function from a to b, is a relation from a to b in which every element of a appears exactly once as the first of an ordered pair. We write f of little a is equal to b when ab is in the function, and we say that b is the image of a. So this definition is absolutely consistent with the definition you learned in algebra in high school. We also have a drawing where we can draw set A and set B, and we say f maps elements of A to elements of B. We call the set A the domain. That is our input to the function. And we call the set B our range. Those are the values that get mapped to by f. So we also say that here B is the image of A, and the subset of B that gets mapped by f is the image of the function. Or another way of saying that is f of A is a subset of B, and that's the set of images under f. We also say things like f takes an input A and transforms it to an output, f of A. In this case, it's equal to B. Another way of saying this is f maps A to B. So now we have the question, how many functions are there from A to B? So the next question is, how many functions are there from A to B? Essentially, we have a set A, and it has some number of elements, say for example 3. And then we have a set B. It has elements that we can map to, however many there are. So the definition of a function says that every element of A appears exactly once. So we consider our first element of A, and we have the cardinality of B choices to map to. We do that for our next element of A, and so on. So basically, we're using the product rule, and we have the cardinality of B choices, and we are doing that for every element of A. So this is the number of functions from A to B. An example problem, determine if the following are functions. Our first example is x-y pairs, where x and y are integers, and y equals x squared plus 7. So is this a function from the integers to the integers, since x and y are supposed to be integers? And the answer is yes. For every value of x, you get exactly one value of y. Our next example is x and y pairs, where x and y are real numbers, where y squared is equal to x. So the question is this a function from the real numbers to the real numbers? And the answer is no, because you have, for the value y equals 4, you have two possible values of x. The last question, A is related to B, where the cardinality of A is 5, and the cardinality of B is 6, and the cardinality of R is 6. So we have some function A, set A, mapping to a set B. There are 5 elements. There are 6 elements here. And our relation has 6 pairs. So here's possibly 1, 2, 3, 4, 5. Well, to get a second pair, you're going to have to use some element of A 2 times. So this is not a function, since the cardinality of our relation is greater than the cardinality of our domain. A function is called one-to-one, also injective, if each element of B appears at most once as an image of A. In other words, everything in B can have at most one arrow, one thing mapping to it. So that means if you have a function from A to B and it's one-to-one, if f of A is equal to f of A1 is equal to f of A2, in other words, the image of A1 and A2 are the same in B, same element of B, that must mean that A1 is equal to A2. So here, this is the criteria we use when we do proofs. Our next definition, a function is called onto, also called surjective, if the image of A is equal to B. In other words, F maps all the elements of A in such a way that the entire set B is mapped onto. So another way of saying that, f, a function from A to B, is onto, then for all B, which are elements of B, there exists some A in the set A such that f of A is equal to B. So now it's time to look at some pictures. Here we have a relation from A to B, and actually it is a function because every element of A appears exactly once. Then it's also one-to-one because every element of B appears at most once. It is also onto because there are no elements of B that do not have an arrow pointing to it. So this is a one-to-one and onto. So here we have another function. We can see that it is one-to-one because every element of B has at most one element mapping to it. In other words, there aren't two different elements of A mapping to the same B. So it is one-to-one. But it is not onto, because you can see here, there is an element of B that has not been mapped. So it's not onto. Here we have another function, but we can see it is not one-to-one because there are 2 elements of A that are not equal to each other that map to the same B. So it is not one-to-one, but it is onto. There's only one element and it is mapped to. So this is not one-to-one, but it is onto. And our last function here, it is not one-to-one because we have 2 different elements of A mapping to a single element of B, and it is not one-to-one, and it is not onto because we have this element here that is not mapped. So not one-to-one, and it's not onto. And just for completeness, one more picture. This is not a function. It's a relation, but not a function because we have a single value of A mapped to 2 different values. So now we have some more example problems of one-to-one and onto functions. Determine if one-to-one. So I'm going to remind you of that fact we're going to use in our proofs. To show something as one-to-one, to show a function as one-to-one, we have to show that if f of A1 is equal to f of A2, in other words, these A1 and A2 map to the same element in B, it is necessarily true that A1 is equal to A2. So we'll do our first example. We're going to assume that f of a1 is equal to f of a2. So if we just plug f of a1 and a2 into our functions, what we're saying is 2a1 plus 1 is equal to 2a2 plus 1. We subtract 1 from both sides. We divide both sides by 2, and we see that a1 must equal to a2. So yes, it is 1 to 1. Using the same technique of using this definition here to determine if f of x equals x cubed minus x is a 1-to-1 function, we're going to look at f of a1, what that means if it's equal to f of a2. So plugging into our function, we have a1 cubed minus a1 is equal to a2 cubed minus a2. Now, does that necessarily mean a1 is equal to a2? So I think about this for a moment, and I see that f of 1 is equal to 1 cubed minus 1, which is equal to 0. And if I look at f of minus 1, that's equal to minus 1 cubed minus minus 1. So that's also equal to 0. So no, this is not 1 to 1. And I've proven this by showing this counter example here. f1 is equal to f minus 1, give you both the same image in B. Now we're going to look at the onto, determine if onto these two problems. And again, I'll remind you of the second fact that we'll use for proofs. If a function is onto, then for every element in B, there exists an element in A such that f of A is equal to B. So you can find an A that will map to B. So just rereading this in terms of our function, this is saying for every integer, there exists some other integer such that f of A is equal to f of B. So in other words, if I choose an integer, let's just choose a random integer, we'll call it B. It's an integer. I want to find some other integer. So I want to find an integer A such that f of A, which is equal to, according to our function, A plus 7 is equal to B. But that's easy. So basically A is equal to B minus 7. So in other words, if you give me an integer, I'll subtract 7 from it, and that'll be the A that gets mapped. So this is yes. This is an onto function. We'll do our second problem now, again reading onto in terms of this definition. So B, in this case, is the set of integers, and A is also the set of integers. So for any integer, we want to find another integer such that f of A is equal to B. So again, if you give me an integer B, we want to find an integer A such that f of A is equal to, which by the way, f of A, I'm just going to plug it into my function, 2a plus 3 is equal to B. So you give me a B, I'm trying to find you an A. So we do this, we have 2a is equal to B minus 3, so A is equal to 1/2 B minus 3. So I look at this and I say, well, what if B is equal to, what number do I need? 4, for example. So if B is equal to 4, I have 4 minus 3, which is 1, times 1/2, which is 1/2. So A is equal to 1/2. So, but unfortunately, I wanted an A in my set of integers. So no, it is not 1 to 1. It is not onto, sorry. Because the even integers, such as 4, are not reached. In other words, they aren't mapped. Nothing gets mapped to them. They are not ever reached. So we have discussed relations, functions, one-to-one, and onto. We haven't done Stirling numbers, and this is where we will pick up with our video number 2, Stirling numbers, pigeonhole principle, and function composition and inverses. Thank you for listening, and I'll see you in class. Bye-bye.